Anna Weigandt. When I first talked to her, she was at Michigan, and then in another month, she'll be at MIT. So she's kind of in between Michigan and MIT. So Anna Weigandt was a postdoctoral fellow at University of Michigan for 3 years. And now she'll begin in September as an instructor in the Department of Mathematics at MIT. Her PhD is from University of Illinois, Urbana-Champaign, because she didn't want to leave Illinois until much later in life. She ventured out to Michigan eventually, and now she's coming to Massachusetts. The PhD was supervised by Alex Young, and she worked on prism tableau and alternating sign matrices. So alternating sign matrices are these beautiful combinatorial objects that you'll see in the talk, and yet there's a lot of deep algebra related to them. And so it's a beautiful subject. Anna was an award-winning student and is given many seminars. She's very productive also, like Margaret Ellen, with papers. And she even built her own kayak. That's what I just learned. So isn't it exciting? And the Northeast Combinatorics Network was created as CONE in the 1990s as a way for people from the New England region who are in these little isolated universities far apart from one another to stay in touch with one another with short meetings and seminars. And so it's exactly in line with the mission of the NCN to welcome Anna to this region by having her give us a talk and break the ice. So Gröbner geometry of Schubert polynomials through ice. Welcome, Anna. Thank you.
Thank you, Bill, for the lovely introduction. And yes, I'm very excited to be moving to the Northeast. I'm here, but still in my apartment in these COVID times. But I'm looking forward to venturing out and getting to meet some of you that I haven't met before. Okay, so this is based on joint work with Zach Hamaker and Oliver Pechenik, and also work in progress, which we hope will appear very, very soon on the archive with Patricia Klein. Okay. So click there. There we go. So ice is nice. So first of all, I'm going to tell you about ice. So ice, it really goes back to thinking about water is made up of a bunch of H2O molecules, and an ice model in this sort of study of statistical physics, it tries to explain how these pieces fit together when water freezes into ice. And so often in physics, we make some sort of simplification because the real world is very complicated. And so the 6-vertex model is a 2-dimensional simplification of this problem where we pretend that ice is flat and maybe lives in a square grid. And so when you force these molecules into a square grid, you get kind of 6 different configurations how these frozen molecules can line up together. And then you try to fit them into a grid. And so you draw bonds so that in each of the different configurations, the hydrogens and oxygens, they're located in the same places, but then you can draw so that these bends are happening in different sorts of ways. And you want to make sure that every oxygen gets 2 hydrogens attached to it. So you really have frozen water. But normally when mathematicians are studying these sorts of things, we don't want to draw a bunch of H's and O's all over the place. And so there's kind of a reformulation that you can do. So instead, we like to think about graphs. And so here is a graph where you have kind of this square grid on the inside, and then you have some boundary vertices along the outside. And there's this on the side edges, there's these boundary conditions where you have some arrows pointing in, and on these upper and lower boundaries, you have your arrows pointing out. And then you want to make sure to orient this graph so that at every interior vertex, you have 2 arrows pointing in and 2 arrows pointing out. And so I've drawn kind of the map for how you go from these 6 different types of frozen water molecules to these 6 different types of 2 arrows in, 2 arrows out internal vertex configurations. Okay, so now that I've shown you this, I'm going to make one more reformulation, but it's not so bad. Instead of drawing so many arrows, let's just focus on the arrows that point left and point down. And then of course you can get back the other arrows by just drawing them in once you know which ones point left and which ones point down. And so when you do this sort of reformulation, you get something, often it might be known as an osculating lattice path, but it showed up in kind of a new context in the past few years. And by Lamley and Chimizono, they started drawing these pictures and calling them bumpless pipe dreams. And so this is going to be one of the main combinatorial objects of this talk. And again, there's just sort of a tile by tile, vertex by vertex correspondence. Okay, so bumpless pipe dreams, I'll just actually give you the definition here. A bumpless pipe dream is a tiling of the n by n grid with the 6 tiles pictured below so that pipes start at the bottom of the grid and end at the right. And so these starting and ending conditions are compatible with these sort of boundary conditions from the 6 vertex model. And you might ask, why are they called bumpless? So they're called bumpless because if you're familiar with another type of pipe dream, it has kind of these bumping tiles all over the place, but these pipe dreams do not have these bumping tiles. There's no bumps allowed. Okay, so why do I like bumpless pipe dreams? In particular, they let me write down one of my favorite types of polynomials, the Schubert polynomials. So a bumpless pipe dream is reduced if pairwise pipes cross at most one time. So this running example, it's actually not reduced because these pipes kind of cross too many times. But that's okay. We can look for reduced bumpless pipe dreams, and those are the ones that we'll care about most for the rest of this talk. Okay, so I've name dropped these Schubert polynomials and told you that they're some of my favorite polynomials, but maybe I should explain a little bit why I like these. So if you do Schubert calculus, you're interested in the complete flag variety. And you can think of the complete flag variety as a quotient of the general linear group by the Borel subgroup of upper triangular matrices. And inside of the complete flag variety, there's these special subvarieties called Schubert varieties. And each Schubert variety defines a Schubert class in the cohomology ring of the flag variety. And these Schubert classes form a linear basis for this ring. And then Borel wrote down a nice isomorphism, or say presentation, of this cohomology ring as a quotient of a polynomial ring by some ideal. So this ideal is generated by non-constant elementary symmetric polynomials. And so if you really want to study this ring, instead of thinking about, say, taking cup products of Schubert classes and thinking from a very geometric perspective, if you have some nice polynomial representatives for these classes, then you can do computations modulo this quotient by this ideal. And so LASCOUX and Schutz and Berger, they proposed one nice choice of coset representatives. They called these things Schubert polynomials. And there's also double versions, which are encoding more information. You get back to the singles by setting some y variables equal to 0. And, excuse me. So these double Schubert polynomials, they're coset representatives for classes in Borel equivariant cohomology. So the initial definition of LASCOUX and Schutz and Berger, it was recursive using these divided difference operators. And since this initial definition, there's been a lot of combinatorial work in understanding these polynomials and their properties, and in particular, representing them using combinatorial objects. So in this talk, we'll see a couple of different combinatorial ways to think about these polynomials. Okay, so the first is bumpless pipe dreams. So as I had mentioned, these kind of newer objects hit the scene, and Lamley and Chimizono, as part of their broader work on infinite flag varieties and backstable Schubert calculus, they showed that a special case of what they were doing produced a new formula for double Schubert polynomials. So the double Schubert polynomial, you can take this as a definition if you'd like for this talk. It's a weighted sum over reduced pipe dreams for a permutation W. So just like Schubert classes were indexed by permutations, Schubert polynomials, there's one for each permutation. And so you have to know how to read a permutation off of a bumpless pipe dream. You just kind of label these columns along the bottom row, 1 through n, and then you trace where the pipes land. So for instance, this pipe in column 1, it kind of goes through, it crosses, and it lands in row 2. And then this pipe that starts in column 2, it kind of goes up here and ends in row 1. And so then you get a permutation in one line notation. And so you look for all the reduced bumpless pipe dreams for your favorite permutation. And then we want this polynomial. It's going to be a polynomial in a bunch of x and y variables. That's why the x and that y are bolded, indicating there's an alphabet of a lot of variables. But you get these products of binomials by just looking at where the blank tiles of these bumpless pipe dreams are. And so, for instance, we have a blank tile in row 1 and column 1, which is going to give us this binomial x1 minus y1. And we have this tile in row 3 and column 3, which gives us this x3 minus y3. And so we multiply these binomials and then we sum over the different bumpless pipe dreams for our permutation. Okay, so I should pause. Are there any questions about this formula? Okay. So there's a nice way to kind of generate bumpless pipe dreams starting from one very special bumpless pipe dream. So if you want to write down actual Schubert polynomials, it might help to know a little bit about this procedure. I'm going to be a little bit hand wavy though, just for time, but you can start from this very important bumpless pipe dream called the Rotha bumpless pipe dream. So this is the Rotha bumpless pipe dream for 4, 2, 6, 1, 3, 5. And it's the unique bumpless pipe dream, which has none of these sort of upward hooks. Thank you. I see there was a question in the chat, reduced bumpless pipe dream, and then it's been answered by Guillermo. Okay, so cool. But this Rotha bumpless pipe dream, it has none of these sort of upward hooks. And if you know about the Rotha diagram of a permutation, this really is kind of on the nose how one might draw the Rotha diagram. And so then you can kind of start drooping pipes. So maybe you take this pipe and you bend it down. This is where I should probably scribble a little bit. So we take this pipe here and we kind of droop it down to say this position here. And when we kind of bend that pipe down, we get to this new diagram here. And so you can look at ways to kind of locally bend pipes, and you can produce all the different reduced bumpless pipe dreams for a permutation in this way. I'm not going to be precise again about this definition of when exactly you're allowed to droop. You kind of can't cross too many things. But if you're interested, we can talk a little bit more precisely in the problem session. Okay. So if you've studied Schubert polynomials, you're probably much more familiar with an older theorem. I put down Fomin-Krylov, Bergeron-Billy, but really this is coming out of work of like Fomin-Stanley and like Billy Jockish-Stanley. There's just a whole lot of combinatorics surrounding Schubert polynomials kind of exploded on the scene all at once. But for our context, the version that we probably want is most closely related to Fomin-Krylov, but if you draw them more like Bergeron-Billy did. But the double Schubert polynomial, it's a weighted sum over reduced pipe dreams. So no bumpless here, just pipe dreams for W. And here, I'm not really going to tell you so much about how to draw pipe dreams, but they kind of have always these upward elbows along this anti-diagonal, and then you have some crossing tiles, you have some bumping tiles, and again, you can look at how to trace out these permutations in a reduced sort of way. And in a similar way, we're going to get products of binomials, but now the things that really matter are the positions of the crossings in these pipe dreams. So the blank tiles, well, here they're always just the same. They no longer matter. But the crossing tiles, for instance, we have this crossing in row 1 and column 2, row 1 and column 1, which gives us x1 minus y1. And then row 3 and column 1 gives us x3 minus y1. And so it's a very, on the surface, similar sort of theorem to this newer theorem of Lamley-Chamazono, but the underlying combinatorial objects are different. And if we stack these, if we stack these different formulas up side by side, you'll notice that there's no way to line them up kind of combinatorial object to object in a way that preserves both the X weights and the Y weights at the same time. So these are genuinely different expressions for the same polynomials as sums of products of binomials. But of course, if you specialize the Y's to 0, there is sort of a monomial binomial correspondence if you just care about the X's, but maybe lining these up, you have to do a little bit of work and pass through some combinatorial work to line them up together. So the sort of thing that you might do is described in a paper of Dao-Ji Huang. Okay. So I should mention that this formula that Lamley and Chimizono came across, again, coming from kind of this geometric perspective with like this backstable Schubert calculus, it was actually hiding, if you squinted really hard, at an unpublished preprint of LASCOUX'S. So LASCOUX, he gave a formula for growth and decay polynomials using objects called alternating sign matrices. So growth and decay polynomials, they are this K-theoretic generalization of Schubert polynomials. And in this paper, Bumpless Pipe Dreams and Alternating Sign Matrices, I connected these two perspectives and gave a bumpless pipe dream formula for growth and decay polynomials, again, heavily influenced by what LASCOUX did in his preprint. So the problem session is actually going to focus in a lot on alternating sign matrices, but maybe in a different context. But I'm going to just tell you what they are and how they're connected to bumpless pipe dreams. So an alternating sign matrix, it's a square matrix so that its entries are in the set -1, 0, 1. And within rows and columns, the entries sum to 1. And then the non-zero entries in each row and column alternate in sign. So for instance, in this row here, we start with a 1, then we have a 0, which we kind of ignore, and then we alternate to a -1, and then we're back to a 1. And so, yeah, there was this, this beautiful enumerative conjecture of Mills, Robbins, and Rumsey a few years back, and it remained open for about 10 years until it was solved independently by Zeilberger, and then Cooperberg kind of used this ICE perspective. But there was a lot of combinatorial interest, especially surrounding this, this enumerative question. Okay, but the reason we like them, one of the reasons we like them today is that they're in simple bijection with bumpless pipe dreams. And so the map is to take this kind of downward elbow and change it to a 1, this upward elbow and change it to a -1, and then the rest of these turn into zeros. It might look like you're losing information, but you're actually not. It's enough to just know these elbow positions, and then it's kind of determined how you fill in the rest of this picture. So it's an honest to goodness bijection. So LASCOUX was working with these pictures and kind of flipped upside down and K-theory, and but if you again kind of straighten it out and look at it in the right sort of way, you can show that his way of associating permutations to alternating sign matrices is compatible with the natural way you would kind of read them off of these pipe dreams. Okay, so there'll be, again, more about alternating sign matrices in the problem session, but maybe from a POSET theoretic perspective. So if you like POSETs, you might want to tune in. Okay. But yeah, so now I talked a lot about the ICE part of the title, and I'm going to switch gears and change to Gröbner geometry. So what do I mean by this Gröbner geometry? There's going to be this family of affine varieties that's going to be important for us today. And so I'm going to start with kind of their defining ideals. So if you fix a permutation, you can get this Schubert determinantal ideal in this ring that's generated by variables coming from a generic matrix. And I'm not going to give you like the precise definition now. You can find that in the problem session, but I'm going to give you just a hint of an efficient way to write down generators for these ideals using Fulton's generators. So what you do is you start with the Rotha pipe dream for your permutation. And then you look at the blank tiles and you fill in the blank tiles with some numbers that are telling you how many hooks appear to the northwest of that tile. So these are all zeros. There's no pipes above them. Here's a 1 because we have one pipe kind of above it. And then here's a 2 because there's 2 pipes that are having their hooks sort of northwest. And then once we have these numbers, what we're going to do is we're going to take minors of size 1 bigger than those numbers. So this is kind of like these numbers are telling us, I really want, say, this submatrix here that starts all the way up at this top corner and ends at this bottom corner. I want this submatrix to have rank at most 1. And so the way I'm going to make that happen is I'm going to carve out some 2 by 2 minors in this generic matrix. Or if I really want this submatrix to have rank at most 2, I'm going to carve out some 3 by 3 minors in here. If I want these sort of blue entries to be rank at most 0, then I'm going to carve that out by just throwing some variables into my ideal. And so these Schubert determinantal ideals, they're prescribing certain rank matrices on sort of maximal northwest submatrices of your matrices living in some big affine matrix space. Okay. And why we like matrix Schubert varieties is they're telling us something about these actual Schubert varieties that we're living down in the complete flag variety. So there's this map where we take the general linear group and we map it down via the projection map to the flag variety. And we can also include the general linear group into the space of n by n matrices because, well, an invertible matrix is just a matrix. And we can use these maps to take the Schubert variety, which is living down in the flag variety. We can pull it back along the projection. We can include it into matrix space and then take its closure. And this thing is called a matrix Schubert variety. And so Fulton showed that the Schubert determinantal ideal is prime and the matrix Schubert variety is the vanishing of this ideal. So these Schubert determinantal ideals are exactly the right conditions to define these matrix Schubert varieties. Okay. So let's do something, I don't know, strange with one of these Schubert determinantal ideals. What we're going to do is we're going to fix a term order on our coordinate ring that is an anti-diagonal term order. So this means if you take any matrix minor of this big generic matrix, the lead term is going to be the product of the things on its anti-diagonal. So that's all an anti-diagonal term order means. And then we're going to compute the initial ideal, this ideal generated by the lead terms of all the things that live in your original ideal. And then we're going to take its primary decomposition. So again, it's a recipe, a weird recipe, but just let's do it. Okay, so the example of choice is 2, 1, 4, 3. It has just 2 generators. And when we take lead terms, well, we're going to take Z11 has this lead term. Here, the lead term is this product of things on the anti-diagonal, and they share no variables in common, so we can be fairly assured that we had a Gröbner basis to start with. There's no weird S-pair computations to do. So here, this is actually the initial ideal. We take its primary decomposition. It actually has a prime decomposition, this intersection of 3 primes. And the picture, how does the definition of the ideal depend on, so yeah, we might go a bit more into this in the problem session, but you start with this Rotha bumpless pipe dream, and then you take, say for this example, since there's a 0, we're going to take 1 by 1 minors in this submatrix, so that gives us this. And then this 2, we're going to take 3 by 3 minors in this submatrix, which gives us this. And I didn't really give you a proper definition, so it's very sensible that you wouldn't know right away. But I wrote out the definition in more detail for a slightly more general case in the document that I'll distribute later. Okay, So, but for now you can take it on faith. This is this particular Schubert determinantal ideal. And so we're gonna take its primary decomposition. We get these three primes intersected together. So no primary things to worry about, just prime. So now what we're gonna do is, these primes, they're kind of coordinates of the variables generating these monomial primes. They actually line up with pipe dreams. So if you look, we have kind of Z11, Z31. This is telling us put these crossing tiles in these positions. This Z11, Z22 says put crosses in those positions. And then, so this isn't just a fluke of this example. This is what happens in general. And this is the lovely theorem of Knudsen and Miller. So they showed that Fulton's generators are a Gröbner basis for the Schubert determinantal ideal under any anti-diagonal term order. And the ideal is going to be this intersection over pipe dreams of monomial primes, where kind of the variables defining these primes are determined by the crossings of the pipe dream. And in particular, this means that the initial ideal is radical. So this theorem was kind of mind-blowing because these pipe dreams, they were pre-existing combinatorics. And there's no reason at all that they should show up in this maybe specific, but this geometric context. But they did. They popped up in this Gröbner degeneration as exactly the right things to index components in the limit. So this is just a spectacular find of theirs. Okay, and indeed it tells us even something stronger. It tells us that these Schubert polynomials, which were a choice of coset representative, they're kind of natural in another way. So each matrix Schubert variety, it defines a class in torus equivariant cohomology. And to compute this class, you can use this sort of axiomatic approach. You can degenerate, say, with a Gröbner degeneration, and the class stays the same. Additivity says that over kind of maximal components, maximal set theoretic components, you can just kind of add up these T equivariant classes, and normalization tells you that coordinate subspaces, it's really easy to write down their classes. They're going to be products of binomials in sort of the way that we've been seeing with these combinatorial weights. So again, this is not enough information for you to absorb these axioms, but you should kind of connect it back to that recipe that we just did. We degenerated, we took this intersection of primes, and then from these primes, we can maybe read off products of binomials in the way that we would with the pipe dreams. So Knudsen and Miller and Ferré-Romani kind of independently, they showed that the T cross T torus equivariant class of the matrix Schubert variety is the double Schubert polynomial. And also through kind of this theory, once you know that this T cross T equivariant class is this Schubert polynomial, it's telling you that this double Schubert polynomial is also representing the right class downstairs in Borel equivariant cohomology of the flag variety. So you know that you're getting this coset representative. Indeed, it kind of identifies this in a unique way as a good coset representative, because this T cross T class is uniquely identified upstairs as being special in some sort of way. So Ferré-Romani, they kind of showed that these things satisfy the divided difference operators that LASCOUX and Schützenberger used. Knudsen and Miller, they used this Gröbner geometry approach and again gave a geometric interpretation for these combinatorial pipe dreams. So not only are the polynomials geometrically natural, but also the combinatorics of pipe dreams is special in this sort of way that it's picked out by torus equivariant cohomology. Okay, so Yeah, but if you're me, probably the first term order that you think of is not an anti-diagonal term order. It's diagonal, like Lex reading order. In English, I read left to right, top to bottom, and that's, yeah. So yeah, what's known about diagonal degenerations? So Knudsen, Miller, and Young, they worked out an analogous story for diagonal degenerations of a special class of matrix Schubert variety indexed by vexillary permutations. So these permutations that avoid the pattern 2143. And so they showed the following. They showed that Fulton's generators are a diagonal Gröbner basis if and only if your permutation is vexillary. So outside of that case, they kind of no one knew a Gröbner basis at the time. And in this case, primes in the limit are indexed by combinatorial objects known as flagged tableau. And they also had a theory of another type of pipe dream that one might call diagonal pipe dreams. So that was the story with vexillary permutations. Here's just kind of an example. We can take this vexillary permutation 1, 4, 2, 3, and its Schubert determinantal ideal is defined by 3 minors. And then if we take the initial ideal, well, these are Fulton's generators. The diagonal terms are going to be the lead terms, and this happens to be Gröbner. So we can just take the lead terms of these generators. We can do the prime decomposition, and what this is going to tell us is kind of these primes, if we plot out sort of what spaces of the grid these occupy, these are giving us kind of these diagonal pipe dreams, but these are also sort of, you can't really see it because the example's so small, but these are Young tableau satisfying certain flagging conditions. So if those words mean things to you, great, but I'm not going to get into like how the flagging actually works, but kind of these are flowing by, I'll drop another buzzword, these excited moves, if these are things you like to think about. Okay, but what's kind of cool is these are also in bijection with bumpless pipe dreams. So when you're in the vexillary setting, bumpless pipe dreams, kind of their blank tiles are exactly these diagonal pipe dreams of Knudsen, Miller, Young. So this kind of leads you to wonder, well, what can you say about diagonal Gröbner degenerations of non-vexillary permutations? And so one of the first things that you might do is an example. So 2143, it's the smallest permutation that fails to be vexillary because, well, it contains the pattern 2143. This is no longer a Gröbner basis, but we can kind of just cancel out the terms in this minor that have Z11. And then the lead term is now going to be sort of this product Z33, Z21, Z12. And so this is actually the initial ideal here. We take its prime decomposition and we see bumpless pipe dreams. So the variables that we're seeing defining these primes are telling us the blank tiles of some bumpless pipe dreams. So this is a very leading example. You might be tempted to say, oh, great, we get a prime decomposition given by bumpless pipe dreams. That's, well, maybe the world's not so kind to us. There's kind of this pathology that shows up with, oh, sorry, this should be a D here, not an A diagonal. So the initial ideal, it might fail to be radical, which means that you still have a monomial ideal, but it's not a square-free monomial ideal. And the world just gets a little bit more complicated. But that pathology kind of lines up with something that happens with bumpless pipe dreams, in that you can have 2 different bumpless pipe dreams for the same permutation that have the same set of blank tiles. And so if you kind of use Macaulay 2 and analyze this example for 321,654, you'll see that the set theoretic component corresponding to this prime shows up in the scheme defined by this, this degeneration with multiplicity, and it shows up with multiplicity 2. So the combinatorics here are now telling you how to read off multiplicity of set theoretic components in the limit. So this is part of that sort of additivity axiom that I was sweeping under the rug, but you're really doing additivity with this scheme theoretic multiplicity. So this highly suggestive example says maybe bumpless pipe dreams are really the right sort of thing to understand these limits up to their sort of set theoretic components with multiplicity. So this is what Zach Hamaker, Oliver Pachenik, and I conjectured. Bumpless pipe dreams label set theoretic components of the diagonal degenerations with multiplicity. Here I have a more precisely, but maybe you should spare yourself the more precisely for time. Just remember kind of that first bullet point slogan. Okay, so what's actually known? Zach Hamaker, Oliver Pachenik, and I, we proved a special case of the conjecture for a class of permutations called Banner permutations, which generalized this vexillary case. And then work in progress with Tricia Klein, we've proved a stronger statement from which the conjecture follows as a special case. And so I might take just a couple more minutes to walk you through sort of an example that illustrates this stronger statement. So the theorem of the work in progress is that if you have an intersection of distinct Schubert determinantal ideals of the same height, then bumpless pipe dreams in sort of the union taken over these permutations label components of the scheme theoretic limit of this intersection of ideals with multiplicity. So it just looks a little bit more technical, but it's just saying that you look at all the bumpless pipe dreams for all these permutations, you were intersecting their determinantal ideals, and that's going to tell you multiplicity of primes in the limit. Okay, so tiny example, we can intersect the ideal for 2, 1, 3 and the ideal for 1, 3, 2. When we intersect it, we actually get a principal ideal just generated by this one thing. And if we have a diagonal term order, then kind of the lead term is coming from this diagonal term from this minor, and then just gets multiplied by a Z11. So now this lead term, it's not square free. So the limit's going to fail to be radical, but that's okay. It's really telling us that the multiplicity of this prime, this Z11, is appearing with multiplicity 2. And this Z22 is appearing with multiplicity 1. And this is mirrored in the combinatorics of these bumpless pipe dreams. So this is kind of analogous to what happens with diagonal term orders and pipe dreams, but you never see multiplicity for this anti-diagonal term order setting. So this is something analogous, but a little bit more complicated to analyze. Okay, so problem session, quick pitch. The main focus of the problem session is going to be a generalization of Schubert determinantal ideals indexed by alternating sign matrices. Here, they're showing up in this story as bumpless pipe dreams and in an entirely different way as affine varieties. So I'm going to give you kind of a hint about a one-step Gröbner degeneration that Tricia Klein and I use to kind of develop a recursion that lets us understand these diagonal Gröbner degenerations. And then I also have some open problems, which maybe you can come see the document if you're interested. It'll be available, but for time, I'll go ahead and say thanks and see you in a bit.
Great, thank you very much, thank you. Unmute to applaud, or you can just use your silly hands up in your icons here. So this is really great. We've got 2 great talks, but before we go to the problem session, there's time for questions. Does anyone have a question? Just unmute yourself or raise your hand if you have a question.
Yeah, is there any analog of this problem for other groups of Lie type?
Oh, so there's definitely like people have been thinking about, I think, analogs of matrix Schubert varieties in like especially work of like Marburg and Pawlowski and Hamaker maybe. So I think there probably is some sort of story there, but it certainly hasn't been worked out for this these diagonal degenerations. But definitely Marburg and Ploski, they study Gröbner degenerations for sort of anti-diagonal degenerations of generalizations of these matrix Schubert varieties. But maybe for like, maybe it's still type A, but involutions. That's probably the better answer. Yeah, but there's more work to be done.
More question?
Just type A, you say?
Yeah, so I think I really should have been saying that's more like K orbits type story. Yeah, so yeah, K orbits and type A. But yeah, in other Lie types, I should maybe just say I'm not as sure what, but not a lot has been done, certainly with diagonal degenerations, nothing.
Anyone else? So I'm sort of thinking as a student here, Anna. Algebraic combinatorics has this amazing ability to take algebraic questions or questions from other parts of mathematics and encode them as these really simple looking combinatorial things like, these diagrams, pipe dreams, and alternating sign matrices. If I'm a student and I don't know any cohomology, or I don't know term orders and Gröbner bases or equivariant cohomology or flag varieties, are there still problems that I can attack if I come to your problem session just as a combinatorialist?
Definitely. So the maybe it's misleading from this talk, but the first few problems in the problem set are about this coset of alternating sign matrices. And so in a very concrete way, we'll be able to define this coset and then start asking about the structure of these sorts of things. So hopefully there will be things for you to play with. There might be some ideals and some taking prime decompositions, but just come hang out and yeah, I'll be there.
Cohomology is optional. Okay.
Yeah, so really we're not going to get into cohomology at all. Yeah, and more thinking about ideals defined by polynomials in some polynomial ring.
Great. Well, thank you very much. Let's thank Anna once again. And